So this is a continuation of my previous video tutorial. In the last video, we saw how to characterize a device, power electronic semiconductor device, and we went through the data sheet, as you can see here, this particular IGBT with anti-parallel diodes, and we extracted the necessary data for the thermal modeling into the PLECS environment. But the example that I showed you was a half bridge, and that actually didn't convey a realistic meaning. That means we had considered a heat sink, but we connected it only to one device. But in practical situations, this is a little different. For instance, if we have an inverter, two-level, three-phase inverter like this, we'd have three different legs. As you can see here, 1, 2, and 3 for 3 phases. And each of the half bridge then would be mounted on a heatsink, be it air-cooled or liquid-cooled. So here is an example image. You can see, you can consider this to have 2 IGBT modules with anti-parallel diodes. And this complete module is then integrated with this heatsink. In this case, it is extruded air-cooled device. That means it may be a forced air cooling or natural air cooling. This IGBT plate is then mounted on the heatsink. And this same thing would be repeated 2 more times for the other phases. So as you can see, I have implemented a more realistic model of the IGBT modules. So the description inside each IGBT and diode is the same as we went through in the previous videos. They're exactly the same. I have considered the heatsink parameters for each module. So you see, we have 3 IGBT modules with integrated heatsink impedances here. It might be a little confusing that I have the heatsink here over the module itself, and I have the thermal chain described externally. So this is how PLECS works. You need to add the thermal impedances of the heatsink external using these connections. You can also take the inbuilt thermal resistances and thermal capacitances and build the ladder network or chain network as you wish, depending on which version of the thermal model you consider. I still stick to these thermal chain parameters and input the same RC pairs that I used in my previous simulation. And all of them are then parallelly connected and ultimately connected to the environment. If it is a water-cooled system, this should be representing the temperature of the water, or it is the temperature of the air if it is the air-cooled system. To modulate the voltage source inverter, so this is 3-phase 2-level voltage source inverter. We have a DC link voltage. This time I have taken the voltage level of the DC link to be 900 volts. This is having no meaning at all, so I can just uncomment it or comment it so that we don't need this value. And for the modulation, we have still 2 kilohertz of frequency, the switching frequency, and the reference frequency is 50 hertz. So I'm building up the modulation blocks here. You can also watch one of my previous videos in inverter sections where we went in details about the modulation techniques. So principally, I have taken a modulation index of 95%, and then we have 3 signals generated inside one sine block, all 180-degree phase shifted. And we have the modulator signal, which is the triangular wave, and the amplitudes I've considered between ±1. Frequency fs is specified. In order to build the triangular wave in PLECS environment, we need to have a duty cycle of 0.5. Depending on other duty cycles, it can be a sawtooth or other form of triangular waves. You can read in the help section how to construct other different triangular waves. But for triangular ones, the duty cycle is 0.5. Once we have it, we can continue with the simulations. Yeah, for the AC side load, you can see I have considered an RL load, and these are described here. This is the M file where I initialize the variables, as I mentioned. Say this particular load has 50 milliohms and 1 millihenries of inductance. This time I consider a more realistic, or I would say it depends on where the converters are installed. I take an ambient temperature of 40 degrees Celsius. Since I want precise simulation results, I have taken the simulation time step to be 10 milliseconds. We can go even more precise, but this is enough for me. And a refine factor for the smooth curves I have considered to be 5. Total simulation time, I take 300 seconds so that we can also observe the thermal stability. So here are some additional settings in Diagnostics tab. Sometimes for some specific points of operation, you might have the negative switching losses. That means if for a particular operating point, the values are read from the loss characteristics as we modeled, if they hit a negative value, sometimes they throw an error. You can suppress this error by choosing warn and crop or crop. I have chosen warn and crop so that I can see the warning at least. And loss variable limit exceeded, you can also select as a warning. I select OK. Let's now run the simulation. Let me show you where I call my initialization file. So this M file, it must not, or it doesn't have to be a MATLAB file directly. If you don't have the MATLAB license, you can also use the Octave scripting as well, which is an open source program. With the same coding, the syntax is the same. You can just initialize. You will see in future tutorials how important this is to use such a scripting for initialization, especially if you need to debug or if you want to find very quickly among hundreds of variables the specific variable that you want. So to run this, we have to save this in the same folder where I saved my PLECS file, and then run. Under parentheses, we have this apostrophe signs and the name of the initialization file with .m extension. Okay, if we run them, if everything is fine, it should be running. So let's check our PWM generation. So these are the 3 sine waves and then the triangular waves all in one. Yes, 95% of the modulation, so the amplitude is 0.95. Here we have the IGBT junction temperature, conduction losses and switching losses, etc. Let's look at the output window. So what do we have here? We have the resistor voltage, resistor current, and the phase voltage. As you can see the curves here, so the total current that is being generated by that voltage source inverter is, RMS value is 950 amperes. and the voltage is 375, phase voltage 375 RMS value. You see the steps here in the phase voltage. One is 0 voltage, then VDC by 3, which is 300, and then 2 VDC by 3, which is 600. Here we can see the line voltages and currents. So here again, if we measure the RMS value, the line current here with 950 as we just saw, and the line-to-line voltage is 650 volts. And the reason it is called the two-level inverter, you see in the voltage, output voltage of the inverter, we have two levels. Is it 2 levels or 3? 1, 2, 3. I need to check. I don't remember what I mentioned, but you see the voltage levels are changing from plus VDC to minus VDC. So these are the generated outputs. Let's now look into the losses or heat losses, or what's called the total losses generated by the module A, B, and C. So all three are separated here and shown in this scope. So steadily it's going to reach the final value, but it needs some time because we have chosen the time of the simulation to be 300 seconds for a proper thermal stability. We'll come back to it. Let's check some other characteristics. What do we have here in the probe? It's for IGBT2, junction temperature, conduction loss, and switching losses. So I have taken from leg 1 IGBT2, that is the bottom IGBT. So we have the junction temperature, switching losses, and conduction losses. So you can see at the beginning, we have the temperature to be 40 degrees, ambient one, as we mentioned. And then with each current impulse or current flow on switching, the temperature increases and cools down for a certain period when it is not on, and then again increases. Repeatedly it continues. These are the periods you can clearly see. These are the loss area. One is for the conduction loss, as you can see. The second one is conducting, but of course with switching. And then this is the switching losses in the form of half sinusoids. So these are in terms of watts. So it's the power loss. What do we have more? Also should have the diode parameters. So let's check for IGBT2 the diodes, or maybe here as well. Yes, let's take the first diode and IGBT from leg 1 and see their characteristic curves. The first two are for IGBTs. That means when IGBT is conducting, diode is blocking. How to see that? We need to look into curve 1 and 3. So these are the voltages. You see when the IGBT is conducting at 0 volt, the no, I have to check again. It took me a second to look into the curves again. So we need to consider in terms of current as well. You see when the current in the IGBT is flowing, then the diode is blocking here and vice versa. The voltages are also alternating. If the IGBT is blocking the positive voltage, there's 900 volts, then diode is blocking minus 900 volts, and alternatingly. What do we have here? Same IGBT diode, and here are the junction temperatures. So it's reaching slowly the steady state value. What's the maximum value we have at this point? 123 for IGBT and 113 for the diode. Comparable. I'll come back when the simulation is finished. So the temperatures have reached to more or less a steady state level, and maximum temperature in that case we can measure for IGBTs at around 125 degrees and 115 for the diode. Maybe 2 or 3 degrees more if we waited exactly 300 seconds, but this is it. I think I explained everything that I wanted to for this particular tutorial. Thank you for your patience and thank you for watching this tutorial. Thank you.